In this video, we're going to focus on resonance structures and how to draw them. So let's begin. Now, what you want to keep in mind is when you draw your arrows, you need to draw it from a region of high electron density, which is basically the nucleophile, which is electron rich, to a region of low electron density, which is the electrophile. It always flows from high electron density to low electron density. The same way as water, it flows from a high position to a low position, like from a mountain down to a low value. Things flow from top to bottom. So here's an example. Let's start with the carbonate ion Lewis structure. So let's say if you want to draw the resonance form of the carbonate ion. There's three resonance forms, but let's just draw one of them. Now this oxygen has a negative charge, so it's electron rich. So we're going to start the arrow from there. It can donate a pair of electrons, form a double bond, and those electrons are going to flow towards this oxygen. So this is like a region of high electron density, and here we have a region of low electron density. The arrows are basically pointing in this general direction. And so here's the Lewis structure for the carbonate ion. This is simply one resonance form for it. As you can see, the double bond can move between three oxygen atoms. Try this example. So let's say if we have a resonance stabilized carbanion intermediate. It's one carbon away from a double bond. How would you draw the resonance structure for that particular carbanion? Feel free to pause the video and try it yourself. So we're going to start from the region of high electron density, which is the carbanion. It has a negative charge. It's more nucleophilic than the double bond. So this carbanion can form a double bond, and this double bond is going to push two electrons on that carbon. And so this is how we can draw the resonance form of that particular carbanion. As you can see, the negative charge jumped 2 carbons. It started on, let's call this carbon 1, and now it's on carbon 3. Try this example. Let's say if you're given the phenoxide ion, which is the conjugate base of a phenol. Now, there are 3 other resonance forms that we can draw from for the phenoxide ion. Feel free to pause the video and draw as many resonance structures as possible that you can think of. So we're going to start with the region of high electron density, which is the oxygen, and it has a negative charge, so it can form a double bond, causing this double bond to push a lone pair on that carbon. So as you can see, the negative charge, it jumped by 2 atoms. So now it's on this carbon. And so we have a double bonded oxygen atom, which is now neutral. Now this carbanion can move here, pushing the lone pair on those electrons. And so now we have this particular resonance form. So the negative charge is now on this carbon. And here we have a double bond. So now this carbanion can move here, pushing another charge on that carbon. So that's the 4th resonance form. So now we have a double bond here, here, and here's the negative charge. And what we can do is redraw the original phenoxide. So this lone pair can form a double bond, pushing those 2 electrons back on the oxygen, giving us the original phenoxide ion. So whenever electrons are free to move, it's said that the electrons are delocalized. They're not attached to one particular atom. They're delocalized around the entire molecule. Okay, so round 4. Feel free to try this example. So let's say if we have an allylic carbocation, which looks like this. Draw the resonance form. So the arrow is going to start from a region of high electron density to a region of low electron density. We can clearly see that the the carbocation, which is the red positive charge, um, is the region of low electron density. It's the electrophile. Therefore, the double bond, which has pi electrons, is electron rich. That's the nucleophile. So we're going to start the arrow from the nucleophile to the electrophile. So this double bond is just going to move here. And that's all you got to do to draw the resonance form for this particular allylic carbocation. So now let's try another example. Let's try the benzylic carbocation. So you should be able to draw 3 additional resonance structures. So go ahead and try it. The first thing we're going to do is take the double bond and move it towards the plus charge. So the plus charge is going to jump 2 carbons each time. So now the double bond is here, and the plus charge is 2 carbons away towards the direction from which the double bond came from. And now we can draw another resonance form. So now the double bond is here, and the plus charge is 2 carbons. It moved 2 carbons counterclockwise. And then to draw a final resonance form, we can move it here. And so now we have this particular resonance structure. And the plus charge is now on that carbon. And we can draw the original structure if we move this double bond back here. So now we're back to where we started from. And that's it. So keep in mind, these two are identical, by the way. So there's really 4 resonance forms for the benzylic carbocation. So here's the next example. Go ahead and draw the resonance form of an amide. So here, there's no positive charge, there's no negative charge. So where should we begin? What we need to know is that the carbon that's part of the carbonyl group, the carbon that's attached to the oxygen and the nitrogen, is partially positive, and nitrogen is partially negative, and oxygen is partially negative. So let's see. We said that electrons flow from a region of high electron density to a region of low electron density. So should we start from the oxygen or from the nitrogen? Let's assume if we should start from the oxygen. Let's just see what's going to happen. If we take a lone pair and put a bond here, this won't be possible because we're going to have 5 bonds on carbon, and carbon can't have 5 bonds. At most, it can only have 4. So we can't use the electrons from oxygen. Instead, we have to start with the NH2. It has a region of high electron density relative to the carbon, and here's what's going to happen. If we use the lone pair from nitrogen, form a double bond, we can break this bond, so therefore carbon can maintain its valency of 4 bonds. So now we have a double bonded nitrogen atom, which is attached to 2 hydrogen atoms. So now nitrogen carries a positive formal charge, and oxygen now has a single bond, but it has 3 lone pairs, so oxygen has a negative formal charge. I guess this is a good point to or a good time to go over formal charge and how to calculate it. Here's a simple equation that you can use. Formal charge is equal to the number of valence electrons minus the bonds and dots that you see. So let's analyze nitrogen for a second. On the periodic table, nitrogen is found in group 15 or group 5A. So therefore, nitrogen has 5 valence electrons. In this structure, it has 4 bonds, no dots. So 5 minus 4 plus 1. That's why nitrogen has a positive formal charge. Now, if we analyze the oxygen atom, oxygen is found in group 16 or group 6A of the periodic table. So it has 6 valence electrons. And in that structure, it has 1 bond, 6 dots. So 6 minus 7 is negative 1. So we have separation of charge. By the way, which of these resonance forms is the major resonance contributor? Basically, which one is more stable? It turns out that the one that's neutral overall is the one that's more stable. Here we have separation of charge, so this is the less stable but more reactive form of the amide. Excuse me. Okay, so now let's try our next example, which is a carboxylic acid. Go ahead and draw the resonance form of a carboxylic acid. So just like before, we know we're going to use this lone pair. You want the electrons to move towards the double bond. If you have an atom with a lone pair, so in this case, this oxygen is going to donate a pair of electrons, and then this bond can break so that carbon can maintain its 4 bonds. So now this oxygen has 3 bonds and it has a lone pair. So now it has a plus charge. So the formal charge calculation will be 6 minus the 3 bonds and 2 dots, so 6 minus 5 plus 1. This oxygen has 3 lone pairs, so now it has a negative formal charge. So clearly this is the more stable resonance contributor. This is the less stable or minor resonance contributor because of the separation of charge. Now what about this example? Let's say if we have an alpha beta unsaturated aldehyde. How would you draw the resonance form for that particular molecule? Now whenever you have a carbonyl groups tend to be electrophilic, so the arrows usually flow towards the carbonyl group, and that usually works generally speaking. I'll give you an exception soon. So this double bond can move here towards the carbonyl group, and that pi bond is going to break. So now we have basically an enolate ion, which is an oxygen with a negative charge that's directly connected to a double bond. And so this carbon now has a plus charge because it lost electrons as that bond moved away from it. And so this is the more stable resonance form because it lacks separation of charge, and this is the less stable resonance form. Here's another example. Let's say if you want to draw the resonance form of this particular carbocation. Here carbon has 3 bonds, so it has a plus charge. So in a situation like this, the oxygen can donate a pair of electrons to make a triple bond carbon, because carbon, it can accept a pair of electrons. Here this oxygen is partially negative, carbon is positive, so because carbon can accept another bond, this oxygen can donate a lone pair. This is called the acetylenium ion, which is used in Friedel-Crafts acylation reactions, and now the oxygen has a positive charge. In such a circumstance, that's when oxygen can donate a pair of electrons. Because carbon won't have 5 bonds. Let me give you another example. So let's say if not this structure. Okay, so now let's say if we have another C double bond O group. How would you draw the resonance structure for this particular compound? So in this case, because there's a double bond next to this carbon, we can use a lone pair to form a triple bond. Only because we have a double bond, this bond can break and push 2 electrons on that carbon. So in that case, the carbonyl group, the oxygen, can donate a pair of electrons to the carbon atom, because carbon in this example can maintain 4 bonds. If it forms 5, it's not going to happen. So now this oxygen has a positive formal charge, and we have a carbanion on that particular carbon atom. So that can work, but this is the less stable resonance contributor because of the separation of charge. Go ahead and try this example. So let's say if you have a nitrile and a carbanion right next to it. How would you draw the resonance form? So clearly the carbanion is the region of high electron density. So we're going to start with the carbanion. It's going to form a double bond, causing this triple bond to break. And so now what we're going to have is something that looks like this. We're going to have a double bond here and another double bonded, a carbon double bonded to a nitrogen. So now nitrogen has 2 lone pairs instead of 1. And so now it has the -1 charge. Try this example. So here we have a carbanion intermediate. Go ahead and draw the resonance form. So this carbanion can form a double bond, and that pi bond could break. So now we have a double bond here and a single bonded oxygen atom. This is known as the enolate ion. You'll see that in Orgo 2. You'll see it a lot actually. Okay, go ahead and try this example. Let's say that carbon has a positive charge and this oxygen has 2 lone pairs. So oxygen is partially negative. So it's electron rich. So electrons will flow from the oxygen towards the electron poor carbocation. And so this is the resonance form of that substance. So now the oxygen has a positive formal charge. So let's say if we have the conjugate base of the phthalimide molecule. This reagent is associated with the Gabriel synthesis reaction. Go ahead and draw the resonance form for it. So nitrogen is the region of high electron density. The carbonyl groups, they can accept a pair of electrons, so they're electrophilic, which means they are the regions of low electron density. So electrons will flow from nitrogen towards the carbonyl group. So we can draw 2 resonance forms, but we'll draw just one for this example. It can also move towards the carbonyl group that's on the bottom. So now we have a double bonded nitrogen atom, and we have a single bonded oxygen with 3 lone pairs and a negative charge. Nitrogen has 1 lone pair now, and it's currently neutral. So this is the resonance form for that particular anion. And for our last example, we're going to have a resonance stabilized carbanion that's next to an alkyne. So what can we do for this structure? So this carbanion can form a double bond, causing a triple bond to push 2 electrons on that carbon. So now what we have is something that looks like this. There's a double bond here, another double bond, but we have a negative charge on this carbon. So that's it for this video. By the way, in that process, that's how alkynes can isomerize under strong basic conditions. An alkyne can convert to an alene, and allenes can convert back to an alkyne, but in a different position. When you get a chance, check out isomerization of alkynes. A terminal alkyne can move and become an internal alkyne under extremely basic conditions. So that's the end of this video, and